What does it mean?
Hey Justin, you remember how Penn told us to come up with the video idea?
Oh, hey Nick. Yeah.
Well, I was just thinking, what are you doing?
What do you mean?
Okay. Anyway, I think I came up with a new video idea, so let me show you. It's pretty simple. Pick a number.
How about 3?
3, all right. So 3, so we use the rule for odds. We use the rule 3x plus 1. And for evens, we use the rule of divide by 2. So in this case, 3 is odd, so we multiply times 3, add 1. That's going to give us 10. That's even, so we divide by 2. That gives us 5. That is odd, so multiply times 3, add 1. That's 16. 16 divided by 2 is 8. Divided by 2 is 4. Divided by 2 is 2. Divided by 2 is 1. And then 1 is odd, so 1 times 3 plus 1 equals 4. Divided by 2 equals 2. Divided by 2 equals 1.
I see. So it just gets stuck in a loop of 4, 2, 1.
Yeah, that's the main point. For any number, it results in this 4, 2, 1 loop that just keeps repeating over and over and over again. And this is called the Collatz Conjecture.
So this really works for any number.
Yeah, any number.
Sounds like a great video idea, but we've got to go. I forgot to read the cereal box this morning.
Oh, no. Grab the chalkboard. Okay, so here's what we're going to do.
Uh-huh, I'm ready.
Okay, so you're going to start with putting the Collatz Conjecture in the top left. Then we're going to all right. Did you get all that?
Yeah!
All right, come on, let's go.
Hey, we got a problem for you. Oh, great. Come on in, guys.
Here you go.
Oh, thanks.
Here we're going to look at the Collatz conjecture. So this comes from 1937 and someone of the name L. Collatz. So this is a really well-known conjecture, but let's review what it says. So we want to define a function t from natural numbers to natural numbers by the following rule. So t evaluated at n is n over 2 if n is even, and it's 3n plus 1 over 2 if n is odd. And then what the conjecture says is that for all n in n, there is a k in n, where if we evaluate n k times with the function t, we end up at 1. And since we've got powerful computers nowadays, this has obviously been checked to a high degree, and it has. It's been checked up to the number 2 to the 68. And I'd also like to point out that this is sometimes called the shortcut function. Maybe in popular media, this conjecture is written a little bit differently. It says that you start with a natural number. If it's even, you half it. And if it's odd, you multiply by 3 and add 1, and then iterate that process. So if you have an odd number, you multiply it by 3 and add 1, you will most definitely get an even number, which means the next step is guaranteed to be this division by 2, which is why we can put this all together into a single function. So what's the outline of what we'll do here? Well, we'll start out with an example of what's going on, and then we'll give a very loose argument for why we expect this to be true, and then we'll look at some generalizations. And by generalizations, I mean we'll change the set of numbers here that this function is defined on. So we'll start with all integers, and then we'll move on to the Gaussian integers. So let's look at our example first. And our example is chosen off the fact that numbers of the form 2 to the n minus 1 are very slow to turn into 1, if you will, by applications of t. So that means maybe we should look at an example of a number of the form 2n minus 1, but it probably shouldn't be too big. So let's maybe pick the number 15, which is equal to 16 minus 1 or 2 to the 4 minus 1. So let's see what we get. So if we start with the number 15, so I'll just write an arrow to mean we're applying this function t. So applying this function t will give us 45 plus 1 over 2. So we multiply this by 3 and add 1. That's because 15 is odd. But let's see, that's 46 over 2, which is the number 23. And that's another odd number, which means we have to do this rule again. So if we do that rule again, we'll get 69 plus 1 over 2. So that's 70 over 2, which is 35. Again, another odd number, so we have to keep going. So applying this rule again, we'll get 105 plus 1 over 2, which is equal to 106 divided by 2, which is 53. Another odd number, so we're going to use this rule again, which notice has the overall effect of these numbers growing. So at the moment, these numbers are getting bigger and bigger and bigger, which is further away from the number 1, which may seem a little bit problematic. So let's apply this rule again. So if we multiply this by 3, we'll get something like 159 plus 1 divided by 2. But that's nice because that's 160 divided by 2, which is the number 80. And 80 is a multiple of 8. And since it's a multiple of 8, that means that we can apply this halving rule a few times. Okay, so if we divide that by 2, we'll get the number 40. If we divide that number again by 2, we'll get 20. Again by 2, we'll get 10. Again by 2, we'll get 5. And we're back at another odd number. But even though we're back at another odd number, this number is quite a bit smaller than what we started with. But since we're back at an odd number, it means we have to use this rule again. So let's do that. So 5 times 3 is 15 plus 1 divided by 2. That's 16 divided by 2, which is 8. And now we're in really good shape. And that's because we have a power of 2. If we divide by 2 here, we get the number 4. We're allowed to divide by 2 again to give us the number 2, and divide by 2 again to give us the number 1. And we have finally achieved the number 1 here. Let's also notice that it took a bunch of steps. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total steps to go from the number 15 to the number 1, which I think is pretty interesting. Maybe another thing to point out is, what if we kept going? What if we gave this to a computer and we didn't tell it to stop at the number 1? Well, the number 1 is odd. If we apply this rule to an odd number, we'll get 3 times 1 plus 1. That's 4 divided by 2, which is 2. So that takes us back to the number 2. So that creates something that's called a cycle for this function. So we've got this cycle which goes from 1 to 2 to 1 to 2 to 1 to 2 to 1 to 2, so on and so forth. And in fact, this conjecture is equivalent to saying that the only cycle for this function in the natural numbers is given by this trivial cycle between 1 and 2. Okay, now that we've got this example taken care of, let's maybe look at our loose argument for why we expect this to be true. Now we'll look at our loose argument for why we expect this to be true. And this is taken from a paper by J. Ligarius called The 3x plus 1 Problem and Generalizations. So if you Google that, it's pretty easy to find. And I believe that you can have access to it for free. I couldn't find the place that it originated. Okay, so how are we going to do this? Well, we'll start with an arbitrary odd natural number. You might say, well, why an odd natural number? That's because the interesting thing is going on here when we have an odd number, because we get growth. And growth is like kind of bad. It gets us further away from the number 1. If we start with an even natural number, then we divide it by 2. That's closer to the number 1. So we want to see like how bad it can be. Okay, so anyway, let's get into it. So let's suppose that n naught is odd. So like I said, we've got an odd natural number. And then next we'll apply t until we get another odd number. So let's say that until we have another odd. And I'll give that odd a name, and that will be n1. And then essentially what we want to do is calculate the expected value of n1. And in order to motivate our argument, let's look at the following, I'll just say diagram or picture. So let's start with n naught. Okay, so the first thing that we'll do is apply our function, but since n naught is odd, we need to apply this rule. So that means after applying our function, we get something like 3 times n naught plus 1 over 2. And now there are two possibilities. This number could be odd, or this number could be even. If this number is odd, we've achieved another odd, and we'll kind of take this out of the loop and call it n1. And then we're done. But if this number is even, we need to apply our function again. And so applying our function to an even number, we'll half it, and that'll give us 3 n naught plus 1 over 4. And then we'll repeat the process. So if 3 n naught plus 1 over 4 is odd, we'll assign that to the number n1. But if it's even, we'll apply t again, giving us 3 n naught plus 1 over 8. And I think you can see where we're going here. If this is odd, we'll assign that to n1. But if it's even, we'll turn this into 3 n naught plus 1 over 16 by applying t again. So let's maybe just point out that these arrows are all applications of t. And then these arrows right here are like assignments. So here, let's put that. We'll say assign. And what I mean by assign is we're assigning n1 this value right here. So now let's maybe make a chart of possible values of n1, and then the probability that those possible values actually occur. Let's see what we've got. So the first possible value is 3 n naught plus 1 over 2. What's the probability that occurs? It is 1/2. And that's because you start right here. You've got a 1/2 probability this is odd, in which case we get this value, a 1/2 probability that it's even, in which case we do not get this value. So the probability is 1/2. The next possible value is 3 n naught plus 1 over 4. What's the probability that this happens? Well, we have to use the multiplicative rule. So we've got a 1/2 probability that we had to go along this branch, and then another 1/2 that we go up here via the assignment, giving us a total probability of 1/4. Then we move on to the next. Our next possible value is 3 n naught plus 1 over 8. Then again, by the multiplicative rule, we've got a probability of 1/2 we go along this branch, a 1/2 that we go along this branch, a 1/2 that we go up here, that's 1/2 cubed or 1/8. And then we can put one more thing here, maybe 3 n naught plus 1 over 16. The probability of that is 1/16. And then that continues on and on and on. And now by a geometric series argument, if you sum the probabilities of these infinitely many possibilities, you get the number 1. So that means we have all of the possibilities. Okay, so this is good. Now let's take this information and then we'll compute the expected value of n1 from this chart. Okay, so now let's calculate the expected value of n1 based off of what we saw on the last board. So let's recall that it has a value of 3n plus 1 over 2 with a probability of 1/2. And then it has a probability of 3n plus 1 over 4 with a probability of 1/4. And then so on and so forth. So that sets up this infinite product. So I'll write down the next couple as well. We have 3n plus 1 over 8 to the 8th. and then 3n naught plus 1 over 16 to the 16th. Like I said, that's an infinite product. Okay, now it's going to be hard to deal with these plus ones, so let's approximate this. And remember, this is not a proof. This is an argument for why this is expected to be true. So it shouldn't be so bothersome that we're leaving off these plus ones via the approximation. So that's going to give us 3n naught to the half plus quarter plus eighth plus 16th dot dot dot. So again, that's just also using some exponent rules. And then what do we have in the denominator? Well, we'll have 2 to the half times, I'm going to write this instead of as 4 to the 4th, I'll write this as 2 to the 2 over 4. And this next one, instead of 8 to the 8th, I'll write it as 2 to the 3 over 8, just so that I have the same base for all of these. And so that next one will be 2 to the 4 over 16. The one after that will be 2 to the 5 over 32. And that's an infinite product like that. So next up, we see that the sum of this geometric series right here is the number 1, just by standard rules for geometric series. So that'll give us a 3n naught in the numerator. And then in the denominator, we'll have 2 to the power, let's see, this is going to be the sum as k goes from 1 to infinity of, let's see what it is. It's going to be k over 2 to the k. Okay, but we've calculated this sum several times on the channel before. I'll let you guys look up some of those videos if you need to, but that's equal to the number 2. So in the end, we have 2 to the 2 in the denominator, which is 4. So this gives us 3 over 4 times n naught. So if we start with an arbitrary odd, then the next expected odd is smaller than the one that we started with. So the argument goes like this. That means that our expected next odd will be even smaller and smaller and smaller and smaller and smaller, but that gives us a decreasing sequence of odd natural numbers. But any decreasing sequence of odd natural numbers ends at the number 1. Now that we've got this loose argument for this conjecture, let's maybe go ahead and look at some extensions. Maybe the first extension we'll look at is exactly like this, except we'll replace n with z. Okay, let's jump into that. So let's see what change we have if we replace the natural numbers with the integers for this function. So the first thing that I'd like to observe is that these following sets of integers are disconnected under this function. What do I mean by disconnected? I mean there's no path using the function t from one of these sets to the other. So I've written it like this. The set of all negative natural numbers gets mapped to itself by our function t. The set containing the number 0 just gets mapped to itself under the function t, and then the set of all natural numbers also gets mapped to its set. So another thing that I'd like to note real quick is that there's no loop or cycle at the number 1. And that's because t evaluated at -1 is equal to -1. Or maybe it's a cycle of length 1 instead of a cycle of length 2. It's a fixed point, if you will. And then another thing that I'd like to observe is that there are at least 2 more cycles. So let's work out one of them explicitly, and then I'll leave you with the other one to check on your own. So let's start with the number -5. So let's observe that -5 is odd. So that's going to leave us with -15 plus 1 over 2, because we need to multiply by 3. But let's see, that's going to give us -14 over 2, which is -7. Then if we apply our function t again to this, we'll get, let's see, -21 plus 1 over 2. So that's going to be -20 over 2, which is -10. Oh, but look, we've already got a loop. Now our next thing to do is divide by 2, because -10 is even. And so that takes us to 5. So we've got this nice loop or cycle between the number 5, the number -7, and the number -10. So let's see, this would maybe be called a 3 cycle because it takes 3 times to go through. And so there's one more, or there is at least one more, I should say, and it starts at the number -17. The next value is -25. The next value after that is -37. And then finally, after several more steps, it loops back to the number -17. And why do I say that there are at least 2 more cycles instead of saying that there are a lot more cycles? Well, that's because the generalized Collatz conjecture says that these 2 cycles, along with this fixed point, are the only new cycles when you introduce the negative natural numbers or the integers here. Okay, nice. So let's maybe get rid of this, and then we're going to look at an extension of this involving the Gaussian integers. So we'll finish this video off looking at a generalization of this map on the Gaussian integers. So let's recall that Gaussian integers are all numbers of the form a plus bi, where a and b are integers, and then I is the imaginary number that squares to -1. So it's defined as follows with the following 4 possibilities. So we get a over 2 plus b over 2i if they're both even. So if we're allowed to divide both of them by 2, we'll do that. And then if one is odd or both are odd, we either add 1 and multiply by 3, add I and multiply by 3, or add 1 plus I and multiply by 3. So that can be summarized as follows. If a is odd and b is even, we have 3a plus 1 over 2 plus 3b over 2 times I. If a is even and b is odd, we have 3a over 2 and 3b plus 1 over 2 times I. And then if a and b are both odd, we have 3a plus 1 over 2 plus 3b plus 1 over 2 times I. And in this case, there is no real conjecture as to how many cycles there should be, and it looks like there are potentially infinitely many cycles. And there's a nice paper by G. Kuczynski that talks about this kind of stuff and lists a lot of the cycles, I think up to length 400. It's called Cycles for the 3x plus 1 map in the Gaussian integers. So maybe as a last hurrah for this video, let's work out one of the cycles that's given in that paper. So it starts with the number 3 or 2 plus 3i. So let's see. In this case, the imaginary part is odd and the real part is even. So that means we still multiply the real part by 3, but we need to multiply the imaginary part by 3 and also add 1. So in the end, that's going to give us 6 plus 10i over 2. Again, 3 times 2, 3 times 3 plus 1. Now we divide that by 2 and we get 3 plus 5i. But now let's notice that both of those are odd, which means we'll multiply each of them by 3 and then add 1. So 3 times 3 is 9 plus 1 is 10. 5 times 3 is 15 plus 1 is 16. So we have 10 plus 16i over 2. So let's see, what's that? That's going to be 5 plus 8i over 2. Okay, then where do we go from here? Well, this 5 is odd and the 8 is even. So that means our map looks like 15 plus 1, which is 16, plus 24i over 2. But let's notice that's equal to 8 plus 12i. But now both of these are even again, so we can just divide by 2. That gives us 4 plus 6i. Both of those are even again, and that gives us our original number of 2 plus 3i. So let's see the cycle length here. We have 1, 2, 3, 4, 5. So that's a cycle length of 5. And like I said, there's a bunch of cycles that you can find in this paper if you'd like to. Okay, that's a good place to stop.
I swear. They don't like, they don't comment, they don't subscribe, they don't even subscribe to the Patreon. Like, I wish there was a way that we could communicate to them to help support the channel, you know, help it grow.
No, that's just impossible. There's no way to do that. I wish we lived in a world where we could just set up some lights, a camera, and film a little short to tell people to do those things, but we can't. So yeah.
Oh no, I'm stuck on a table. If you don't like, comment, subscribe, I'll fall down.
That's so dumb. That is probably the stupidest one yet. That's like what a 5-year-old would come up with.